So what does it take to visit a website? If you are opening up your computer for the first time for the day and you want to visit a website, you want to go to Google or you want to go to whatever website it is that you want to visit, how are you going to do it? I'm going to walk you through what it takes. What does your computer go through when you visit a website? And we are going to start with this beautiful network diagram. Over here on the left is you. You are a laptop that is not yet connected to the network, but you are about to be. And whether that connection is wireless or wired doesn't matter. What matters is you're not connected and you are about to be. And over here on the right, we have the website that you want to visit, www.is404.net. What a beautiful website it is. So let's go through what is it going to take. What do we want to do? We want to open up a browser, go to www.is404.net, hit enter, and then watch this beautiful website. Look at that. It's just such a spectacular website. Watch what happens when it loads. All the things that are going to go into that. So what's it going to take? What does it take to make that happen? First, we have to do DHCP, the Dynamic Host Configuration Protocol, to connect us to the network. Next, we're going to have to do some ARP, Address Resolution Protocol, to find the MAC address of the next hop of all of our packets. Then we're going to do some DNS name resolving that name of www.is404.net into an IP address. This IP address is still a mystery to us, so we are going to have to type in www.is404.net and get to the website that we want to go to. Then we're going to have to use the Transmission Control Protocol, or TCP, to make the connection between us and our ultimate destination. We're going to have to do some network address translation because we can't have private addresses on the public internet, and we're going to have a private network that we're working on, much as many companies and many homes have. And then we're going to use HTTP, finally, to request and send the files that we are looking for, the HTML, the CSS, the JavaScript, and anything else. So now that we've got HTTP, we've got all the protocols that we need, let's talk about what we're going to be working on. Our task here is going to be to fill out this table for each packet, sometimes multiple times as a packet moves across the network, because some of this information is going to change. So at the top layer, we have our application contents. What is the message that we are trying to send? That's really the purpose, right? Is to get data, some information across the network. So what's the information that we want to send? Transport layer, is it TCP or UDP? And what is the source and the destination ports? At the network layer, we're going to use IPv4, but you could swap it out for IPv6. The principles are the same. We've got source and destination there at IP addresses. And then finally, at the bottom layer that we're going to talk about, the data link layer, we have our Ethernet, and we've got our source and our destination, in this case, MAC addresses. And the reason I chose these protocols is because that's what most of us are still using to this day. So this is going to be what most of your network communication looks like, and we're going to go through this. So now we have connected our device, our laptop, to the network. Let's move it up a little bit out of the way so that we can see and pull up our first table so that we can talk about our first packet. What is our first packet? The very first thing that we need to do when we connect to the network is get ourselves some configuration information. And one great protocol for that is the Dynamic Host Configuration Protocol, DHCP. And the very first message in DHCP that DHCP sends is what is called the DHCP Discover. So that is packet number 1, DHCP Discover. We hop on the network, we scream for help, we scream, I don't know who I am, I don't know where I am. And so that is going to be the contents of our message, is essentially, please help me, I don't know where I am. And that is a UDP packet. So DHCP uses UDP, and it uses a source port of 68 and a destination port of 67. Now this protocol operates differently than some of the others. Very often, as a source port over here, you're going to see something from that dynamic range of ports, something from that very high 49,000 to 65,000 range of ports. But DHCP operates a little bit differently. It doesn't choose something from that range, and in fact chooses a source port of 68, a destination port of 67. And so it's sending out a message on the network to destination port 67, hoping that someone, a DHCP server somewhere, is listening and is ready to respond. And with our DHCP Discover messages, we're going to send from 0.0.0.0. Why is it 0.0.0.0? Did I say too many zeros there? I might have. 4 zeros. Why? Because we don't have an IP address. We can't say it's from a specific IP address because we don't know what our IP address is. So we can't say what IP address we are. So we're going to send it from zeros to 255.255.255.255. This is a broadcast. This is a cry for help, and it's sent to 255s because it needs to be a universal broadcast. And this broadcast address works on every single network. So we're going to send that out. I'm going to use in my slides here this little symbol right here. That symbol is going to be to indicate that this message is a broadcast message. So next to each of our messages, I'm going to show a little symbol. These are not universal symbols. This is just a way for me to demonstrate to you this is a broadcast, and we'll see what unicast messages look like in a minute when those start to pop up. So our first message, DHCP Discover, goes out to everybody. Now we need to talk about what happens at the Ethernet layer. What happens at the Ethernet layer? What's going on at the data link layer? So data link layer, Ethernet, we have a source MAC address. We use that MAC address because that's the addressing at that layer. And our source MAC address is going to be our MAC address because we know what that is. AB, 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 AB. So that's going to be our source. What's going to be our destination? Well, we don't know yet. Just like when we're sending our broadcast message at the network layer, we don't know who we're sending it to. At this layer, we still don't know who we're sending it to. So we're going to send it to the broadcast MAC address of FF. I think that's enough. That's all the Fs there. And that's the broadcast MAC address that says, hey, everybody, listen to me. And this message goes out to everybody. But the only one that's really going to be listening is whatever it has an application, a DHCP server, that is listening on port 67. So we've almost got this message sent. It's time to send this message. First, I just want to very quickly, in terms of the rest of this demonstration, these MAC addresses are way too long for me to have to say every time. So we're just going to shorten those a little bit. So in these cases, all of these MAC addresses represent full MAC addresses, but I'm shortening them because I have to say them over and over again. As you have already seen, I'm not great at saying letters and numbers over and over and over again. So we're going to just shorten down to ABAB and FFFF, and the rest of these MAC addresses have all already been shortened. Know that they represent actual MAC addresses, and in a real network you would see the full MAC address, not that in nowhere does a real network use these shortened versions. So we've sent our DHCP Discover. We shouted it out to the network. Who got it? Who received it? One computer received it, at least one, hopefully, as long as we have a DHCP server running on our network. Now, in our case, we are going to use this router right here as our DHCP server. Typically, in smaller networks, and especially in home networks, the router is your DHCP server. It is the one that is listening. It's the one that's going to respond when you get those requests. So our second packet then is going to be a DHCP offer. The second message in a DHCP exchange is the offer. That comes from the server to the client, to the one that is screaming. So what goes into that offer? Well, one of the things that goes in there is the IP address that you're being offered. Obviously, it makes sense that you would receive an IP address when that's the whole point. You want an IP address, so you got an IP address. That reverses these addresses. So remember, it was from port 68 to port 67. The response is going to be from port 67 to port 68, because just like when you're writing a letter and you reverse the sender and the receiver when you're sending the response back, we're going to do that with all of these addresses. Very similarly, but differently, we have our network layer. We have our IPv4 addresses. And in this case, our message back is coming from 10.37.0.1 because that is our DHCP server. That's the machine that is running our DHCP server application. And the message coming back is going to be sent to 10.37.0.5. That is the IP address that was being offered. And in this case, that makes this message, instead of being a broadcast, that makes this message what is called a unicast, a message from one machine to one other machine. But wait a second, you might say, look, 10.37.0.5. My computer up there doesn't know that it's 10.37.0.5. So how am I, poor little computer me, supposed to respond and say, this is me? How am I supposed to know that this message is meant for me? Well, we're going to use the data link layer to know that. And that's how this message comes to me. And my computer recognizes that the destination, ABAB, is me. And so it's going to look at that message and say, okay, this is for me. And it knows, because it's for UDP port 68, that this is a DHCP message, and so it can look at the DHCP message, recognize 10.37.0.5, wait, that's my new IP address. And so with this, we can go on to the next message. Now, very briefly, I want to talk about what else goes into this DHCP offer, because it's not just the IP address. DHCP offers contain a lot of information, and you could do a whole video on this, and in fact I have, but we're just going to very briefly talk about one of the things is that IP address. Another thing is the subnet mask, so that you can determine what your network address is, because that's kind of helpful and important information. You would also have the default gateway, because if you ever want to send something outside of your network, you need to know how to do that. That's what the default gateway is for. So that DHCP server in that offer is going to say, hey, your way off the network is whatever the router's IP address is. It also includes information about the lease time. Some DHCP leases are long, some DHCP leases are short. You might be given that address for 2 hours or 10 hours or 24 hours or 5 days or 3 weeks. It's entirely up to the person who configured the network what that lease time is. And also, often, not always, but most of the time, you're going to receive information about DNS servers, what DNS servers are available on the network. So in our case, all of this information was included in that DHCP offer that we are talking about. I didn't show it on the other chart, but you can know that all of that information is there. Now that we've received an offer, it's time to do the third message in a DHCP exchange, and that is the DHCP request. The DHCP request says, hey, I saw that offer you gave me for 10.37.0.5. I want to accept that offer. And that's what the DHCP request is for. And so the addresses are going to switch again out to 67 back from port 68. The IP addresses swap again. Once again, this is a broadcast. The request is a broadcast to every computer on the network. Why it's that way, I don't know, but it is. And the source, once again, is 0.0.0.0, because even though we are requesting now 10.37.0.5, we don't officially have it yet until the next message comes. So we're still at 0.0.0.0 from 255.255, etc., etc. And this is, once again, a broadcast. And here we're going to just kind of skip on through here. The source MAC address is going to be me. Destination MAC address, because this is broadcast, is sent out to FFFFFFFFFF, and that goes out to everybody on the network. So finally, we are ready to receive the fourth message, the last message in the DHCP exchange, which comes from the router back to our machine, a DHCP acknowledge that says, yes, you can have the IP address that you requested. So discover, offer, request, acknowledge. Now we have an IP address. So let's go ahead and add that to our diagram. So now our IP address, as you can see, is 10.37.0.5, and we're ready to start sending some packets. Well, what packets do we need to send? We need to send DNS. We typed in an address at our address bar, www.is404.net, which is the address over here, but we don't know that yet. We don't know this address. All we know is the name. So we typed in the address, so we're going to put together our packet, our DNS request. And that packet is going to be a DNS request that says, I want the A record, or the IP address record, for www.is404.net. DNS uses UDP, mostly, not always, but we're going to use UDP as our example here, and we're just going to choose a port, a source port. Remember, it comes from that dynamic range, and it goes to port 53. Great. We have our network address, which comes from our address of 10.37.0.5, and it goes to where? Where is it going to go? It's going to go to our local DNS server. And how do we know that it goes to our local DNS server? Because DHCP told us that. In that DHCP configuration, we were given a local DNS server that is this. It could be this, it could be anything, but in our case, our DHCP configuration gave us 10.0.0.53 as our DNS server that we should use for these requests. So we're going to do that. Great. Now, this is a unicast, because it's from one machine to another machine. There's no broadcast addresses involved. And we've got our data link layer. We've got our source address of ABAB. Now we've got a little bit of a problem. What is the data link layer address of the next hop? Because with Ethernet, remember, with Ethernet, we are only concerned with the very next hop. What is the address of the next computer, the next router, the next machine that I should talk to? As I am sending this packet, packet number 5 is coming from my computer. It needs to go to, at the data link layer, it needs to be addressed to whatever address is the next hop along the path. Now, in our case, let's assume we connected to our network. We have 0 things in our ARP cache. Maybe we let the cache expire. It took us 10 minutes before we did anything on the network. And so our ARP cache expired. We have nothing in there. What are we going to do? How are we going to fill out that information and add the MAC address of our next hop? We got to do ARP. So I said this is our 5th packet. That's not true, because we're not ready to send this packet because we need to do ARP first. So let's look at what ARP looks like. Address Resolution Protocol, that's what converts IP addresses into MAC addresses. That's the protocol that needs to come into play. So this is our new packet 5. Packet 5, the DNS thing, that's going to have to be sent out later. So this packet is our new packet 5. That is our ARP request. And the contents of that is who has 10.37.0.1. How do we know that it's 10.37.0.1? Again, because our DHCP told us that. It told us that if our destination address is not within our local network, then we need to send it to our default gateway, which in our case is the router 10.37.0.1. So we're going to send that information off of our network using the information that we have in our DHCP configuration, that default gateway that we were given. And in order to send it there, we need the MAC address of 10.37.0.1. Now maybe we'd have that in our cache already because we've been sending and receiving packets from there, but we're assuming we need to do this resolution. So we're going to do some ARP, and anytime you're going to send stuff to anywhere else, you need to do ARP so that you can get the MAC address associated with it. And there's nothing in the transport layer or the network layer for ARP. So we're going to get straight down. We've got our contents, the who has, that's the ARP request, and we're going to go straight down to the data link layer. This is from ABABAB to FFFFFFF again, because that is going out as a broadcast then to everything on the network. An ARP request is a broadcast that's shouted out to say, hey, who has this IP address? Give me your MAC address. Obviously, we can't send it directly to that device because we don't know the MAC address. That's why we're sending ARP, so we send out that broadcast to everybody. The computer that we are requesting, in this case 10.37.0.1, is going to respond, and it's going to send an ARP reply as a unicast back to us. The ARP reply says that 10.37.0.1 is at CDCD. The MAC address that you're looking for is CDCD, and once again, there's nothing in the transport or the network layers, but at the data link layer, we've got from CDCD, because that's the MAC address of the router on our local network, and to ABAB, that is our 6th packet. That is where that 6th packet comes from and where it goes. And now we have our MAC address, so we can finally fill out that DNS request. So that DNS request, as we already saw, is going to be now our packet number 7. It was 5, but it wasn't quite ready to be sent yet, so we sent ARP instead, and we'll refill in all that information that was there before, and then we'll just add that one little bit of information that we were missing, the MAC address of our next hop router, which is right there, CDCD, and we are ready to send that packet. And that packet makes it all the way to the router before we need to do some more work with it. Because at every hop, those MAC addresses need to get replaced. At every single hop, the MAC address gets replaced with the new MAC address associated with whatever is sending it, whatever in the next hop is receiving it. And so we have a new MAC address, a new source MAC address of EFEF, and a new destination MAC address of now C1:10, which is the MAC address of our destination, which is the MAC address of our local DNS server. So now our DNS server has received the DNS request. It's a lot of work. It's a lot of things that go into making this work. So now we have our DNS request at our local DNS server. What is our DNS server going to do with it? Well, it has to resolve that DNS request. So let's go through the process of resolving that. Let's go through what goes into that. The very first thing, if you're talking full resolution, let's assume that maybe nobody who on this network has ever visited www.is404.net before. What are they going to do? How are they going to figure out what that is? If this is a full resolver, the very first thing that it's going to do is send a packet to the root DNS servers. And I'm not going to put the IP addresses of those, but know that this here substitutes for that IP address. The root DNS server, whatever root DNS server is closest to you, will receive that and respond. And the question that is being asked there is, where is the .NET top-level domain. So if we are going to is404.net, we need the top-level domain servers for is404.net. Or for the .NET top-level domain. So we're going to send out that request to the root to ask for the name servers for the next one. And you'll notice all of this information is there. It's always there. Every single packet that you send goes through this full process. As we saw, ARP is a little bit different because it doesn't have the transport and the network layer, but pretty much every other packet is going to go through this entire thing, and every single one of them is going to have all of these layers of addresses and encapsulation on them. So we send out this DNS request from our server, from 10.0.0.53 to port 53, the DNS port on the root DNS server. And then we address that to the next hop router from us, C110, just like we have here. There's one problem here. We're making the switch now from our private network to the public network, which means that this packet, all of this information over here, needs to be replaced. We can't have the private addresses out on the public network. So what are we going to do when this packet makes it to this router and has to make the switch from being on our private network to being on a public network? We're going to do network address translation. And just a very quick reminder, not going to talk about the whole process, but this has to happen at the boundary between a private network and a public network. Only at that boundary. So before we were moving between routers, but we were still within the private network of 10.0 everything, or 10. Everything is our private network. So we control that. We don't need to address translate until we are moving off of the private network onto a public network. And it converts that private address to a public address and then back again on the return trip. And we'll talk about that whole process. It also changes the port. So in addition to changing the IP address, it changes the ports associated. And I'll show you what that information looks like right here. Right here we have the router's memory as it is changing that. So originally, if we went back and looked again, we would have a message from port 51,251 to port 53 from our private address to the root DNS. Now we have our router has to store that information. It stores the protocol. We were using UDP, the original source. Port 51,251, the original IP address, port 10.10 or 10.0.0.53. It stores the original destination, the root DNS IP address, and the original port, and then it stores the new port, 56,555. Again, this is just going to be some port that it chooses from the dynamic range. That information is stored in the router's memory so that when it receives a response to this message, it's going to know who to send it to inside of our network. Here, the packet gets replaced, the transport layer information gets replaced, the network layer information gets replaced with the new port and the router's IP address right there. And I'm going to maybe not show all of the MAC addresses that go on here, but understand that, again, at each hop, just like happened within our network, also happens outside of our network. With each hop, the MAC addresses are going to change to be whatever the destination is. And so then the root DNS server receives that request. It says, I know where the top-level domain servers are, and it's going to send back a response that says, here's the information, here's the IP addresses of the .NET top-level domain. And the router's memory stays the same. The packet is responding to the packet. Remember, the addresses just flip again, and it comes back, makes its way back to our computer. Now our computer, or our DNS server here, says, hey, now I need to know from the top-level domain servers, where are the name servers for is404.net? So we're going to send out those requests. And that request is another DNS request going to the name servers, going to the .NET top-level domain, asking for the name servers for is404.net. So the top-level domain, .NET top-level domain servers, are storing information about the name servers for all of the domain names associated with that top-level domain. So is404.net, Schetzler.net, Google.net, whatever .NET address you have, all of the information on the name servers for those is here inside the top-level domain servers for .NET. So that request is going to go out. It's going to be a new connection with a new port, in this case 52,525, just another one from the dynamic range. All of that information, and now we're sending it to the .NET top-level domain. And once again, when we get to our router here, as we get to the boundary between the private and the public network, now we need to do the address translation again. And again, I'm not going to show it again, but you know the address translation happens. In this case, we chose the new port of 55,577. So then when the .NET top-level domain responds, it's responding to 55,577 at our router's public IP address of 5.5.5.5. And it's going to respond and tell us the information that we requested. What are the name servers for is404.net? Which is the information about where do I go when I want to get IP information about is404.net. I need to go to the name servers for that. So here we go. Off it goes. It comes back through here. The router retranslates that message just like it did before back to what we need to do here. And we are set. Now we have the name servers, and now we need to send yet another request. So this has taken 3 messages back and forth, one to the root, one to the top level domain. Now finally we have the name servers for is404.net, and we can say to those name servers, please send me the A record, the IP address for www.is404.net. And we set up a new connection to port 53 from port 63,222. We're going to use a new port because we're connecting to a new server to 1.1.2.2 from 10.0.0.53. And we've got our MAC addresses there. That information goes out. It gets translated once again at the router. And the DNS server is going to respond with a DNS response that says, I have the IP address of www.is404.net. Here it is. It's 20.20.20.20. And all those addresses got flipped just as usual. And it gets translated again at the router. It gets back to our server. Our DNS server now finally has the IP address that we are looking for. So now our DNS server has all the information that it needs right here. But now we need to get that information over to our computer. So that DNS server, the next message being sent is going to be message number 14. Finally, a DNS reply that says www.is404.net is 20.20.20.20. The reply to our original request after sending a whole bunch of other requests out to the network is, here is the IP address that you are looking for, 20.20.20.20. That message, once again, goes through here, gets translated, the MAC addresses get converted, not address translated, not what happened here, but we do need to convert the MAC addresses because we're at a new hop along the network, and that message ultimately arrives back at us, and now we know the IP address that we are trying to send to. Finally, we know the IP address that we're trying to send to, so now let's send a message. But we can't just send HTTP because HTTP relies on TCP, and in order to set up a TCP connection, we need to send a TCP SYN. That is a synchronized message to initiate the connection. We're going to send that to port 80 because we're using HTTP and that uses port 80, unless it's encrypted, but that's outside the scope of what we're talking about right now. So we're sending to port 80 to destination machine 20.20.20.20 from whatever random port we choose, 65,534, from our IP address, and we are set. And that packet makes its way across the network, and we replace the MAC address again as we pass through the router. We replace those MAC addresses. We arrive once again, we need to do the address translation at this machine. So we have a new record, a new address translation right here that remembers the old connection information, replaces it with the router's information and a new port, and then finally that message can make its way across the network. It makes its way across the network, replacing those MAC addresses at each step until finally it arrives at the destination. It arrives at the router closest to the destination. The router says, hey, I know where that is. I can send that message to port 80 to 20.20.20.20 to BB08, the MAC address of our server. And we send that. We finally have arrived. We finally sent the TCP SYN. We still haven't sent the data that we wanted, the HTTP message. That'll come later. Because first, we have to do our three-way handshake. The second step of the three-way handshake is the SYN ACK, which comes back through that same path. So as it bounces along, it gets its way, it gets to the router, and the original information is now replaced once again with the internal information. So the external stuff replaces the internal. The router uses its little memory table to remember that information and swap that out. And it bounces its way across our network until finally it arrives. And now we can send our next message, the TCP ACK, which concludes the three-way handshake, establishes the connection. That goes through the whole process again. And now we can finally request the information that we wanted to request. And that is our HTTP message. Our HTTP message is going to be get / and then the protocol number, HTTP 1.1. And then we're going to specify a host. That's the required information for an HTTP request. All of this same connection information remains the same, stays the same here. So as it translates through the router, these ports and stuff are going to stay exactly the same as they were, or as they were in that initial connection. We can send this request. The request goes through the translation, all those things, same stuff happens every time. Just remember the same stuff is happening every time. All that address translation, all the replacement of the data link layer stuff, all of that's going on the whole time. Our packet finally arrives here, our HTTP GET request, and before we can respond, our computer, our server here, needs to send the TCP acknowledge. And so it's going to send an acknowledgement that it received your request. So you sent a request, now I acknowledge your request, and now I can finally send the data that I was interested in. And in that case, that's going to come with an HTTP status code, a 200 OK, because I found the file that you were looking for. All that information gets passed along, all the TCP, all the IP, all the data link stuff gets passed along, gets translated, makes its way back across, and finally we have the web page that we were looking for. There's one more step. We're not quite done, because in order for TCP to really feel complete, it needs to acknowledge, my computer needs to acknowledge the receipt of the response. So I got the HTTP response, I acknowledge that I received the response, send that information back, and finally, we're good to go. So as a quick review, we had DHCP connecting us to the network and getting us the configuration information that we wanted. We have ARP getting us the next hop, allowing us to figure out the MAC address associated with an IP address for what we want to send to. We have DNS for resolving a name to an IP address. We have TCP and UDP, but a lot of our time was spent here with TCP, establishing that connection and acknowledging receipt of those messages. We have network address translation, keeping your private IP address off of the public internet and converting between those two sets of addresses, depending on which network you are talking to. And finally, HTTP for requesting and sending those files, with the GET request to get the files and the response to send the files that we requested. And we did it. We have a web page. That's what it takes. That's what happens every time you visit a web page. Now, DHCP only happens once when you connect, but all the rest of that stuff is going on the whole time, and every time you request a web page, and every time you visit a page. And sometimes when you visit a page and it requests things from other websites, that's happening a bunch of times. And all of that stuff is required to make the web function, to make your browser do the things that you expect it to do. So there's a couple things that we didn't talk about that I want to just really quickly say. This is a topic for another video. Maybe someday I'll make it, or you can find somebody else talking about it. First of all, we don't have HTTPS yet. This was an HTTP unencrypted connection. If you want to do HTTPS, the big difference is that it adds more setup to the connection. So as we establish the connection, we have our TCP stuff, and then we have to have a handshake with HTTPS to establish the parameters of our encryption. That's going to be going on there. Also, this is HTTP 1.1. HTTP 1.1 uses TCP. HTTP 3, the modern standard, uses QUIC, which happens over UDP. That's the differences between TCP and UDP, and the way those work is also another topic for another day. So now it's time to check yourself. Assume I understood that list of protocols. I understand DHCP, I understand NAT, I understand ARP, I understand all that. Could you explain to me the way they work together? So I know what they mean, but can you explain how they work together? What is the order of those packets? What has to happen for me to open up my browser, type a command, or type a website and visit that website? If you understand that, you have a great understanding of what's going on a network.